Hello everyone, I welcome you all in 38th lecture of the course Process Equipment Design, and here we are going to design the evaporator. If you remembered last two lectures, there we have discussed design of evaporator and solve the set of nonlinear equations with the help of Badger-McCabe method as well as Newton-Raphson method. And in this lecture, we are going to illustrate the design of evaporator with the help of examples. So, let us focus on example 1. And in this example, a triple effect evaporator system is used to concentrate sodium hydroxide solution. Operating parameters are given in the table which is shown over here, that we will discuss later. On. In this case, Cp of all feed as well as liquid streams are given as 3 kilojoule per kg degree Celsius, right. And latent heat of vaporization in each effect, that is lambda naught, that is first, second and third effect along with the steam, we are considering that as 2000 kilojoule per kg. U1 is given as 200, U2 300 and U3 500. Okay. So, we have to design this evaporator system with the help of Badger-McCabe method. Okay. So, let us see the parameters. We are given number of effects as 3, steam temperature as 165 degree Celsius, feed concentration 8% by weight and product concentration 35% by weight. So, we have to concentrate. So, we have to design the triple effect evaporator system to concentrate the feed from 8% to 35%. Feed inlet temperature is 110, feed flow rate 25,000 and last effect vapor temperature is equal to 53 degree Celsius, or you may be given here the pressure, that is P3, because last effect is connected with the vacuum pump and that unit and that value is known to you, right. So, as far as feed flow sequence is concerned, it is considered as backward, and if you focus on this backward sequence, feed should enter from the last effect, then to second effect and then to first effect, right. So, if we focus on overall heat transfer coefficient, you see the last effect overall heat transfer coefficient has maximum value and it keeps on decreasing when we move from last effect to first effect, and the reason is very simple. When the feed is entering into the last effect, it is having highest flow rate, right, and when it enters into the second effect, some amount from this feed is converted into the vapor. So, whatever liquid is entering into second effect, it is having less flow rate as compared to the feed, right, and so the case is there for first effect. Okay. So, in this way U1, U2, U3 will vary as per the sequence. If we focus on forward sequence, then U1 will be maximum for first effect and so keep on decreasing till last effect. Okay. So, let us start the solution of this example. Here we are having the schematic where first, second and third effects are shown and feed enters into third effect because it is backward sequence with the flow rate F, concentration XF and at temperature TF, right. So, when vaporization takes place, V3 exits from the top, L3 which is exiting from the bottom is entering into the second effect as it is shown over here, and so L2, and finally we are having the product from first effect and that is L1 and X1. Okay. So, if you consider XF is available at 8% and final product, that is the X1 value is given as 35%. Okay. So, in this way concentrations are known to you, and as far as vapor movement is concerned, feed will enter into the first effect, okay, because movement of vapor will be independent to the movement of feed. Vapor as well as steam movement will always be in forward direction. Okay. So, V1 enters to first effect, V1 generated which is used as a heating media in second effect, V2 is generated which is used as a heating media in third effect, and so V3 will be generated. So, in this way I hope sequence is clear to you. So, let us focus on the solution of it. The first step will be to derive governing equations, because whatever equations we have derived in previous lectures, these are basically for forward sequence. Okay. And as the sequence changes, these governing equations will also change. Okay. So, let us derive the equation first. So, let me first focus on effect 1, and if you see this is basically the schematic of it, and we are focusing on first effect. And when we consider the first effect, whatever stream is exiting, whatever stream is entering like V naught and L2, and the stream which are exiting like V1 as well as L1, all these we have to consider, because we have to make the material energy balance, and for that we basically make an envelope around the system. Okay. And whatever streams are entering into it and exiting from it, that we have to focus on. So, as I am having two stream which are entering and two stream which are exiting, so let us see the material and energy balance. So, if we focus on the enthalpy balance, first of all we consider whatever streams are entering into this, we consider whatever streams are entering into this, that is the first effect. So, I am having L2. So, L2 contains enthalpy H2, that is the enthalpy of the liquid, right. And next is I am having V naught which is entering. So, V naught will transfer lambda naught heat to the system, and that will be equal to V1 capital H1, right. So, when we make the balance for V1, that should be nothing but L2 minus L1. So, I am considering L2 minus L1 capital H1, because that is the enthalpy of the vapor. Okay. And similarly, I am considering L1 which contains enthalpy H1. So, let us elaborate that. Further, I am having L2 H2 plus V naught lambda naught, right. And next I am having L2 minus L1, and we can further elaborate this capital H1, which is basically small h1 plus lambda 1, okay. And that is basically the enthalpy of vapor, which is equal to enthalpy of liquid plus heat of vaporization, fine. And that again add the term L1 containing H1 enthalpy, fine. So, let me rearrange all these, and we can find the equation like V naught lambda naught plus L2 H2 minus H1. So, H2 will come from here and H1 will come from here, okay, when we consider this, right. Further, we will add another term, and that will be lambda 1. Lambda 1 is basically including, lambda 1 basically includes L2 and L1 like minus L2 plus L1, and that should be equal to 0. Okay. Further conversion of enthalpy into CPT, we can find this as enthalpy balance, that should be V naught lambda naught plus L2 Cp T2 minus T1, right. We can expand this term, and then plus lambda 1 bracket L2 minus L1. So, here I am having another term, that is lambda 1, and this should be L1 minus L2, right. In this way we can consider the enthalpy balance, and finally we have the rate equation for first effect, and that should be U1 A1 bracket T naught minus T1, that should be equal to V naught lambda naught. Right now I am considering this as A1, but we assume that each effect consists same area, right. So, finally we will consider that as A, okay. In the similar line, I can derive the equation for effect 2, but as I have derived equation for first effect, I can simply expand that to effect number 2, and for this here I should consider V1, okay. So, that V1 is nothing but L2 minus L1, fine, as you can see over here. So, L2 minus L1 lambda 1 plus L3 Cp T3 minus T2, because L3 is the feed to this, and similarly I am having lambda 2 L2 minus L3, right. and that should be equal to 0, and this is the rate equation, okay, where I have to consider L2 minus L1 at the place of V1, right. So, in this way we can consider equation for second effect, and similarly we can consider equation for third effect as L2 minus L3 into lambda 2 plus F Cp Tf minus T3, because here we have the feed, and similarly lambda 3 L3 minus F should be considered, and this is the rate equation, right. So, in this way we can derive the governing equation of all three effects, and now we will start the solution of these equation using Badger-McCabe method. So, the first step of this method is to decide temperatures of the unknown temperature of this system. Okay. Now, as far as unknown temperatures are concerned, for T1, T2 and T3 we usually know T3, and that is given as 53 degrees Celsius in this problem, okay, and T1 and T2 are unknown to me. Okay. So, we can consider equal heat transfer in each effect, and so we can consider temperature differences. So, let us see the solution of that step. To find out temperature difference of each effect, we should consider total driving force which is available in the system, and that should be T naught minus T3, right. So, 165 minus 53 we can consider as 112, and this 112 degrees Celsius is distributed as delta T1, delta T2 and delta T3, right. So, considering equal heat transfer in each effect, that is Q1 should be equal to Q2 should be equal to Q3, we can find delta T2 by delta T1 which should be equal to U1 by U2, considering equal area of each effect. U1 and U2 values are known to you, so you can consider 2 by 3, and similarly delta T3 by delta T1 should be 2 by 5. Okay. So, when I consider total driving force, that should be equal to delta T1 plus delta T2 plus delta T3. Okay. And further we can consider this as a division of delta T1 into multiplication of delta T1, right. So, this value is usually known to me, and that I consider as 2 by 3 and similarly 2 by 5. So, solving this equation we can find out delta T1 value, and so delta T1 you can obtain as 54.19 degrees Celsius, and that should be equal to T naught minus T1. Okay. Similarly, delta T2 and delta T3 we can find out, because I know delta T1 and I know U ratios, right, U1 and U2 or U1 by U3, right. So, in this way I can find temperature of each effect. So, T1 I can consider using this equation where T naught is available at 165. Okay. So, considering this, T1 should come as 110.81, T2 74.677 degrees Celsius, and T3 will be 53. When you consider the temperature as well as temperature difference, whatever you have calculated, last effect temperature may vary, okay, and variation is very little, like 53 point something, okay, but last effect temperature is fixed quantity that you cannot play with. So, that should always be the given temperature, and that should be 53 in this particular example. Now, once I know the unknown temperature of effects, that is T1, T2 and T3, we should find out the flow rates L1, L2 and L3, and so the V naught. So, let us see how to find it. Now, if you focus on this example, this is basically the backward sequence, okay, and when we consider the product flow rate, and product in this case is the L1. Okay. So, when we consider the product flow rate, we assume that vapor consists 0 solute, right. So, whatever solute is available in the feed, the whole solute is available in the product now. Okay. So, we can make the component balance such as F XF should be equal to L1 and X1. So, here you know f x1 as well as x2. So, here you know f xf as well as x1, right. So, here we can consider L1 x1 should be equal to f xf, and that should be equal to 25,000 into 8% by 35% by weight, right. So, here we can find out L1 as 5714.2857 kg per hour. Next step is to find out L2 and L3. Okay. So, to do that, let us focus on the governing equation again. So, here I am having the governing equation. When I focus on effect number 2 as well as effect number 3 and enthalpy balance of these effects. Okay. So, if you focus on this particular equation, we can consider that here I am having L1, L2, where L1 is known to me, L2 is unknown to me. Similarly, here I am having L3 which is unknown to me. So, L2 and L3 are unknown to me in this term as well. Okay. And similarly, when I focus on effect number 3, L2 and L3 are unknown to me, feed is known to me, and L3 is unknown to me, and L3 is unknown to me. So, what is the meaning of this? If I consider these two equations of enthalpy balance of effect number 2 and 3, I can say that the only unknowns are L2 and L3, right. So, here I am having two unknowns and two equations. So, unique solution will exist which you can solve through simultaneous term, which you can solve simultaneously, okay, because once I know the temperature, these equations become linear in nature, right. So, you can solve these simultaneously, and while solving this you have to put the known parameters. So, let us see that. So, here I am having L2 minus L1. So, L1 value I know now, lambda 1 value I already know, L3 is unknown to me, and so you can find out here, and so you can consider temperature difference, and which you have already calculated previously. Similarly, lambda 2 is known to me and L2 and L3 are unknown to me. Okay. So, when you resolve this equation, you can find the equation as 4000 L2, because here you are considering lambda 2 L2, and here we are having lambda 2, and here we are having lambda 1 and L2. Lambda 1 and lambda 2 values are equal, so it is simply added, and that gives 4000 L2. Similarly, you can find out other term. So, in this way you can find out the equation of second effect. In the similar line, you can find out the equation for third effect putting all values, where feed temperature is given as 110, right. So, in this way you can have these two equation, and unknowns are L2 as well as L3. You can solve these equations simultaneously and find the value of L2 as 11806.104 kg per hour and L3 as 17334.306 kg per hour. Okay. So, once you have L2 and L3 values, you can find out V naught value considering enthalpy balance of first effect, where the term V naught is available alone, right. So, in that case you can find out V naught by solving these equations, because all known parameters are with you. So, value of V naught you can find as 6731.7037 kg per hour. Okay. Now, what is next step? When I know the temperatures of first and second effect, I know the flow rates of all effects along with the steam flow rate. What is next? We should find out area of each effect. Okay. So, for that we will use the rate equation of each effect. So, let us focus on that. Here I am having area A1 for first effect, and that should be equal to V naught lambda naught, that is basically the Q1, divided by U1 T naught minus T1. Okay. So, you know all parameters. V naught should be given as kg per second when I am considering this balance, right. So, here it should be considered in seconds. okay, and lambda naught is given as 2000 and 1000 because it is, and 1000 because this is available in kilojoule, right, and 200 is the U1 value which is available in watt per meter square degree Celsius. 54.19 is the temperature difference, and so you can find out area of first effect as 345.07 meter square, right. In similar line you can find out A2 as 312.24 meter square, and so A3 which is coming out as 283.375. Okay. So, here basically you should consider V1 and here you should consider V2. Okay. Now, once I am having area of each effect, and initially we have assumed that area of each effect should be equal. So, we have to find out average area, and then we will consider that how the area of each effect is deviating from the average area, and so we will revise the temperature difference values, right. So, let us see how to find out average area in the system. So, that you can find out considering this. So, that you can find out considering this equation where A is equal to A1 delta T1 plus A2 delta T2 plus A3 delta T3, and it should be equal to A delta T, right. So, average area we can find as 322.52, and you should consider here that average area is basically on temperature difference weight. Okay. So, we can find out revised temperature difference as delta T1 dash, and from here onward we have second iteration, right. So, delta T1 dash should be equal to A1 delta T1 by A. How much area is deviating from the average area? Fine. So, A1 is this, temperature difference in first effect is this, and the area is this, right. So, you can find out temperature difference in first effect, that is the revised value, and which should be equal to 57.978. So, you can consider deviation in two iteration. In first iteration it is 54.19, in second iteration it is 57.978. So, sufficient deviation is there. Similarly, delta T2 dash and delta T3 dash you can find out, and so temperature of each effect. Last effect temperature will always be fixed at the given temperature, and that is 53 in this example. So, now you have to repeat all steps considering these T1, T2 and T3 values, and next you have to find out L1, L2, L3 and so V naught, and so the area A1, A2, A3, and so the average area, and further you have to see whether deviation is there or not. So, let us see that quickly. L1 is known to me, and these are basically enthalpy balance of second and third effect, and values you can find as we have discussed in previous iteration, and so you can find out L2 as 11760.067 and 17311.28 kg per hour, right. So, further considering enthalpy balance of first effect, you can find out value of V naught, which is coming out as 6662.779 kg per hour, and so you can find out area of each effect. Okay. So, now the area of each effect considering all these value, I am not going into details of this because this point we have already discussed in the last iteration. So, A1 value you can obtain as 319.225, A2 320.093, A2 320.093, A3 323.86. And so, you can find out that these areas are different. Okay. So, next we have to find out average area, and considering these average area as well as the calculated area, you can find out delta T1 prime. You can find out delta T1 double prime and delta T2 double prime and delta T3 double prime, right, because from here I am having the third iteration. Okay. So, you can find these values as, and so T1, T2, T3 as these. Okay. So, if you focus on T1, T2 values from if you focus on T1, T2 values and compare with the last iteration, these values are pretty close to the value which you have considered in last iteration. Okay. And similarly, you have to carry out all iterations. So, maybe next iteration will give the two consecutive value equal, and so that will be the final solution of this problem. Okay. So, I am not going into detail of this, assuming that you can do on your own, right. So, I am having second example also, which I will cover quickly, because here I am having different flow sequence. Okay. So, here again I have to design a triple effect evaporator system to concentrate 15,000 kg per hour of milk from 5% to 40%. Flow sequence is 213, that is basically the mixed. Feed enters at 30 degree Celsius, saturated steam is available at 150 and last effect temperature is 50. Okay. So, total 100 driving force is there in the whole system, and we have to design this using Badger-McCabe method, and here I am having some known parameters. Okay. So, in this solution we have to consider only two iteration, neglecting boiling point rise. This is the flow sequence. This is the flow sequence where feed is entering into second effect, then to first effect and then to last effect, right. So, in this way final product exits from the last effect, and that is L3. So, usually XF and X3 is, so usually XF and X3 are known to you, and let us see the governing equations of this. So, here I am having sequence as 2 1 3. This is the schematic. For first effect you can simply consider L2 H2 because it is entering, V naught lambda 1 as we considered previously, and L1 H1, okay, and so V1 capital H1, right. So, in this way some balance you have to carry out for, so in this way balance you have to carry out for energy as well as mass, and you can resolve the final equation as L2 T2 minus T1 plus V naught lambda naught minus V minus lambda 1 L2 minus L1, right. And so, this is the rate equation U1 A1 T2 U1 A1 T naught minus T1 equal to lambda naught V naught. Okay. Similarly, you can find out enthalpy balance and rate equation for second effect and so for third effect. So, let us quickly cover the solution of this. We again have to find out temperature of each effect. T3 temperature is known to you. So, let us see the temperature of first and second effect considering equal heat transfer in each effect, okay, as we have discussed in previous example. So, I am not going into detail of that, just see how the value can be obtained. Okay. So, delta T1 we can obtain as 27.27 degree Celsius, delta 2 18.18 and delta 3 54.54, right. So, T1, T2 and T3 you can find accordingly as these. As product is exiting from the last effect, you can find out L3 as 10,000 into 0.05 divided by 0.5 because 5% to 50% is total concentration of feed is considered in this example. Let's further we will focus on L1 and L2 calculation, right, as we have discussed in the previous example. So, here I am having two equations which you have to solve simultaneously, and value of L1 and L2 you can obtain as given here, and so we can find out the vapor flow rate, and so we can find out the steam flow rate, that is 3265.19, okay, considering the enthalpy balance of first effect, and now we can find out area of each effect. Okay. So, area of one effect you can simply consider. So, area of first effect you can simply find out based on rate equation, which comes out as 166.299. A2 you can find out as 162.997, and so you can find out A3 as 144.01. Average area you can find as 153.52. From here you can see the deviation, right, and so we require second iteration. So, revised temperature differences of each effect you can find considering average area as well as the actual area, and you can find the value as these. And finally, you can consider, and once I am having these value, you can find out T1, T2 and T3 is fixed at 50 degrees Celsius, and so the results of second iteration you can compile as L1 3974.75, L2 7165.27, V0 3259.66, A1 that A1 that is area of first effect as 153.26, A2 153.06 and A3 153.9, and when you average it, the average is pretty close to these value, and that is 153.55, but still solution is not completed, you have to iterate further, okay, till all 6 parameters of 2 consecutive iterations should be equal. Okay. So, in this way we can design triple effect evaporator system, and here you can find the references, and now we have to summarize the video. So, this summary includes the summary of the lectures 1, 2 and 3 of this week, and it goes as: in these lectures governing equation for multiple effect evaporator system are derived. Design of multiple effect evaporator system using Badger-McCabe method we have discussed, and further we have considered design of triple effect multiple effect evaporator system using Newton-Raphson method. We also focused on vapor liquid separator, whether it is placed vertically or horizontally, and finally we have consider design of multiple effect evaporator system using 2 examples where backward sequence as well as mixed flow sequence are considered. And forward sequence we have already considered when we have designed the triple effect evaporator system, and where we have focused on derivation of each governing equation, right. So, that is all for now. Thank you.